Hi everyone, I'm Homin Jiang from HI Taiwan, and we are a couple of people working on this project. Today I will update you the status of the 16 gigasample per second ADC board. We have our young engineer Chen Yu sitting right there. He's working on this project also. Oh yeah. I will give you a quick introduction first. Okay. Oh yeah, here. And then I'll go to the detail of the chip, 7122 and 7123. Both of them are almost the same, and just one of is the sampling rates go up to 15 gigasample per second, and the other one is go to is higher, is 16 gigasample per second. Then we'll talk to you about the interface in the FPGA. It's mainly a giga transceiver. Then we'll show you the testing result, and also we did some work for the Jasper library, and we are testing the 32 parallel input or 64 parallel input to the polyphase filter bank. Then we'll go to the summary. Okay, we're part of this so-called partnership for international research and education. Is involved in University of Rwanda and outside HIA. I'm not so sure about Germany, and our job is just to develop next generation ADC for this VLBI observation. But we are keep developing this kind of high-speed ADC all the way after the 5 giga ADC. So, and this board will be under the Casper umbrella, so I think everybody can use it. If the ball going well, we are spinning the ball again, and if the ball going well and strong enough, I will put it in the mega spectrometer and put it in a green telescope for that as a testing. Okay, this is the current VLBI digital backend. I think it's those two and 5 giga ADC. This current one. Current one is then using the 5 giga ADC. As the Hanno said, people need more usually. Human beings always need a faster, higher, and further. So we are keeping searching for faster ADC. This table is made by Jonathan last year, and actually there's a lot of faster ADC in the market. You can see from the table, but the price is really high. So we keep using this the Lentec one. The official price is about $2,100 US each. So we are keeping on this chip. And last year, analog device have this 10 gigasample per second 12 bit. I think the unit price is fine, but you have to order a large volume. I take this from the website, but I think the price should go down this year, I guess. I think Luke in Gunbeng not designing on this chip. I think this chip should be good for the NGVLA. Okay, we designed the 10 gig ADC board a couple of years ago, and with Z-Duct connector here. Z-Duct connector here. And this is mainly for those two. Actually, this chip can go up to 12 gigasample per second, but they limited by this parallel VDS output. So that's why we go to a serial ADC. So we need another kind of connector. So we choose FMC. And then another thing for the Roach 2 is Roach 2 is kind of small to accommodate this kind of 32 parallel input. If I try this use those two, and it's almost use about 50% of the resource of those two. This is version 2 of the 15 giga sample ADC. The part number is 7122 and 15 giga sample per second 4-bit. Bandwidth is 18 gigahertz. And it's a FMC connector, so there's many of the platform in the market you can use. We are targeting on using the so-called internal clock for the version 2. So for the internal clock, it can only go up to about 11 gigahertz only. And this board is quite simple, just a SPI control to control the reference voltage of the chip, and then the 4-bit differential CML output to the connector. And the problem of the advanced chip is it's really easy to get burned out. So we burn out many. So then the version 2 it can burn out. So we keep spinning the board. This is version 3. Version 3 we are using 7223, which can go up to about 16 giga sample per second. The others is all the same, and it's a FNC connector, so we are using a VC118. And the difference between version 2 and version 3, we make a frequency divider to divide down this 13 gigahertz to about 500 megahertz as a reference clock for the giga transceiver in the FPGA. This is a detail of the inside the chip. There's a signal input here, and there's a linear buffer, then the 4-bit phase ADC, then there's a thermometer to a binary encoder, and then have a DAC output. The purpose for the DAC output is just for the debugging purpose, and you can measure by the oscilloscope and for debugging is anything wrong with the chip. Then there's PRBS scrambling mechanism in the chip, so there shall be no problem for the DC balance. And then there's a 4 lanes of data output, differential CML interface. Also, then there's a high-speed clock output here. Okay, this is a high-speed serial I/O data output, and this is clock output. Okay. Lastly, I think we were developing this board about 1 year ago, and at that time there's a Skyrod, but Skyrod had no FMC connector, so we had to find one from the market. So that's what we choose in the VC118, and then have I think then have two 100 giga Ethernet output, so it should be good for testing, and the price about 7,000 US is cheap. And then it made by Xilinx, it should be more reliable. And the problem is we have to port the hardware to the Casper. There's a lot of work. Okay, the Atlanta chip is not really follow this kind of serial ADC standard, JSD204. It's some kind between parallel ADC and the serial ADC. So the typical 4 feature of this JSD204 is the DC balance. You have to balance the signal. Usually then use the 4-bit to 10-bit encoding and also PRBS scrambling. Also, there's no clock for this standard. Then embedded the clock in the data stream. Also, then there's a character for the word bonding, and there's a so-called R character, RAQ character for the channel bonding. And there's a PRBS scrambling in the chip, so we don't have to worry about this. And there's no crack. There's no crack of this JSD204. There's no crack signal, but and then recover the crack from this so-called 8-bit to 10-bit encoding, but the Zentek one then don't have this kind of mechanism, so we have to provide a dedicated clock to the FPGA. And then don't have embedded special character for this kind of word bonding or channel bonding. But the good thing is that the chip, the ADC is 1 bit equal to 1 word, so we don't have to worry about this word bonding. And then we have to worry about this channel bonding. We have to go out on the code to make the channel bonding. Okay, there is a sequence of what we did for the channel bonding. The key is to find this leading character or the pure PRBS code. This is 3000, 4000, and you keep searching this special character and memorize the position in the memory. Then you will know the difference between the 4 lanes. So, and you can use the RX line. This is a parameter provided by Linux. So you can shift the data stream earlier or later, so you can align the 4 lanes. This shows you the idea. Usually, the 4 lane come into the FPGA will not be the same clock. So you need to align using the RX line to shift some of them earlier or later, make the four of them just get in the same clock. This is the RX slide provided by the Linux. You can use these parameters to shift the data stream. Okay, this is a block diagram show you what we did in the FPGA, and mainly we are using the so-called Jiang transceiver IP wizard to generate a vertical code, then add some this kind of channel bonding code by ourselves. Then have this so-called SIPO, serial in and parallel out block inside the Jiang transceiver vertical code. This block will cut demarks 1 bit into 32 bits. So totally, the 4 lane input it will create about 128-bit output. Then we're using a 254 to convert this 128 bits into 4 bits. So we can recover the 4 bits from here. Then we using the so-called IOA interactive logical analyzer to take the data into the computer. Then the data in the MATLAB, we can do the Fourier transform. Okay, this will show you the preliminary result from the version 3. We make a 5 ball, and there's a 5 curve of this ENOP. We have an opportunity to optimize this, the yellow curve, this ball number 4, and we don't have the opportunity to tune the other 4 because it's getting burned out. And the ENOP is about 3 bits for the ball number 4. And we can clock in the 16 gigahertz, that's for sure. And this SINET, signal to noise and distortion, is about 22. dB for the board number 4. And then this is spur-free dynamic range for number 4 is about 35 dB. I think some people really want to know the noise power ratio of this board. This is data we taken from version 2. And we clock at different frequency. But mainly the noise power ratio is around 12 dB to 14 dB. Okay, we will keep spinning the board. This time we make a decision to put some protection in front of the chip and in front of the signal input in front of the clock input. And also we make a differential input for the clock. If we want the clock at 16 gigahertz, you need a differential input. Okay, we are working on the yellow block for this 16 giga ADC also. We are still working on. And we tried the 32 parallel input. And I think it's past the combination. If you use the 32 parallel input, that means it's 500 megahertz FPGA clock. It's quite challenging for the timing, I guess. So I tried this 64 parallel input, and it's passed also. And this will slow down your FPGA clock. And I checked the resource, and for the VG118, looks like the VG118 is huge. For 32 parallel input is about 10%. And for 64, it's about 20% used only. Okay, summary. We test with VG118, and we can clock in the 16 gigahertz with a differential external clock. And we are spinning the board again, and we put some protection chip, active device in front of the ADC. Before, because we put this kind of passive device, it looks like it doesn't work. And we also working on the yellow block and just per library. And if you are looking for faster ADC, you can prepare about 300K US dollar, and the Zentech will give you about 30 to 40 chips. And then guarantee you can run 20 gigasample per second, and maybe 25 gigasample per second. Okay, that's it.
We have a couple minutes for questions. Any questions from home?
So those resource utilizations, those were just for the yellow block?
No, the whole thing. The whole thing I show you on here. Yeah, the whole thing.
Oh.
How long does that FFT take to grow when you set the parameters?
FFT to grow? Oh, it takes a while. I forget, pretty long. You can take a couple of copies, I guess. Not just one, a couple of them.
Yeah, we should work on that.
Yeah.
Any other questions?
Well, what's your deployment schedule now? When is your?
I think the new board probably, we are in the layout phase now, probably 2 or 3 months. 2 or 3 months, we will have the new board, I guess.
There's no other questions. One more round of applause for Homin.